Hey everyone, my name is Mohit. I'm an Android engineer at Cash App. I'm also a GD in Kotlin and Android, and my presentation is about building StateFlows with Compose. My presentation is about Molecule. Yesterday, my colleagues, Bill, also gave a presentation. Today, I give another one. Two is better than one. In this presentation, what I'm going to talk about is how to set up and use Molecule, the library. Oh, by the way, does anyone use Molecule currently? Of course. Oh, thank you. That's good, because you're here and you'll learn about Molecule. I'll explain why it's called Molecule. I'll share with you design patterns I use at Cash App with this library in our architecture, and also share how you could go about testing things with Molecule, and also share some bit nerdy things like how it works underneath the hood. And so let's start. So when you think about this talk, the title of this talk, I put a lot of thought in building StateFlows with Compose. When you think of Compose, you may think of the UI, adding text, but that's actually not what Molecule uses underneath the hood. It actually uses the Compose runtime. And so at Cash App, we draw a clear distinction between UI whenever we're talking to each other, Compose UI versus Compose. And Compose, internally, Compose, the core, is a general purpose tool like for managing a tree of nodes. It knows nothing about the UI, but you could leverage it to build different libraries like Compose UI. You could also hook into it to build things like Molecule, like there's another library like Mosaic by Jake. And so it's a general purpose tool for managing a tree of nodes, and these nodes could be anything. And the Compose, what it is underneath the hood, it's a compiler plugin, and that provides you with, there was a talk by Zach on state snapshot system that it provides you could hook into. So Compose UI builds on top of this where the nodes are the views. So Molecule leverages Compose, the core library, underneath the hood. And the way you use Molecule is that Molecule takes in some composable function, and it could be, in our case, we use it for our presenters, and basically this composable function returns you something. In our case, it returns a UI model, some UI state that you want to show on the screen. So you could use this for any different use cases also. You could make this composable function for a different use case, not just for a presenter. But that's what we use mostly, this is Molecule for. And in Molecule, you give this presenter, and Molecule internally sets up something called, I go into a recomposer, the compose runtime. And it sets up recomposition. It gives this composable function to it. And what it provides you, the API of Molecule, what it provides you with is a StateFlow. You could also build regular flows with this also. And you could collect from these StateFlows, and I'll show you how we do that in our architecture. So this is like an overview of 1,000 feet of what Molecule does internally. It's a very simple library. There isn't a lot of logic and not a lot of files. So let me show you an example of using this. So suppose that you had different streams that you were working with, maybe from a remote service or a database. And in this example, I have a user flow and a balance flow. And I want to share the problems that this library solves, right? So you may take an approach where you have a Compose UI view, like a profile screen, and you might, listen to these flows by using something called subscribe as state, give a default value, and then tell your texter to render this data. And there are a couple of problems with this approach. One is that this is a Compose UI view. It has business logic in there. It's dictating what the default value should be. and there's some undesired coupling to these streams of data, and it makes the composed UI view, when you look at this, not reusable. And how do we go about making this composed UI view reusable? We could introduce a presenter, and we have presenters and at Cash App, and I'll go into like how that's set up. So you could have a presenter in which you provide this dependency database. They have a method that returns a flow of some UI state, and this UI state is your loading state or a success state. And what you could do is you could combine these streams together. You combine these streams together, have some business logic in there that produces some type of a UI state. So the good part about this is you're extracting your business logic out, from your view layer, and your view should be as dumb as possible. So you're extracting it out and putting in your presenter. So, but the problem is that when you look at this code, if you were to add more and more logic, you add more, more streams together, it gets very complicated. So we want to be able to, with coroutines, like be able to write code like a little bit more imperatively. And we could do this with Molecule. And what I'm going to do is take that example and convert that to using Molecule. So basically what I'm going to do, create my composable function, which is in this case my presenter, in which I'm providing some flows together, and basically have a model that it returns. And inside there, I could collect from these flows using collect that state and specify some default values. And then I could have some logic to produce some UI state based on what those streams return. So this is a very simple composable function, a very, very simple one that returns some UI model. And the first thing that you need to do in order to use this with Molecule is to be able to first you want to create a scope, which is I'm creating a scope on the main dispatcher, and I'm going to do scope.launch Molecule. So the library provides you with an extension on scope, and there are different extensions. One of them is called launch Molecule. And inside of that launch molecule, so that launch molecule returns a state flow that you could collect from to get what UI state was pushed to the state flow. And the next thing this takes, which is a clock, and I'll go over what are the different clocks that you could use. So it takes in a recomposition clock, and there are two of them. And this is one of them. This is what you would use if you were using it, called context clock. And the next thing that it takes in, the last thing, is your presenter, your composable function. So what happens is that anytime a recomposition happens in this presenter, like anything that's get pushed, and the clock is the signal, and then it pushes a new item out to the state flow. So there's another version of this extension, which is basically this, which takes in a callback. And the callback will get called every time there's a new value get pushed out to the state from this composable function. So this version doesn't really respect back pressure, whereas the other version does. There's another extension. Suppose you wanted not a state flow but a regular flow. You could also get that, like a cold flow. And here, you could use molecule flow method for that. So there are different utilities that are provided to you by this library to use to create flows, to hook into Molecule. So there's a critical piece here. When you look at this, you may think to yourself, well, I could create state flows regularly, but the one benefit is this clock. The one benefit is that you could control emissions by using a clock. And by specifying, frame clock, and that really has consequences in terms of like writing, good tests and handling race conditions in your tests. So it has that's one of the big benefits of creating a state flow in this way. And what do these clocks do? And the clock for me, was something that was challenging to understand. So When you recompose, recomposition means that your composable method calls called again with different inputs, and it produces and it will do the call that it produces some output. So when that happens, what it does when it does recomposition is wait for the next screen, and the pulse signal that does that is called a monatomic frame clock. And a monatomic frame clock is provided to you by Compose. There are different types of clocks, and this is a pull-based system where you have your monatomic frame clock is your pull signal. So in Compose UI, there is a monatomic frame clock. I'll show you that's set when you use it. That sets for you, and the choreographer, like in Compose UI, performs the actual pulling. So. When you're using this library, you're providing some type of a pull signal, and what it does underneath the hood is that it sets up a recomposer and gives basically this frame clock to it. That's the same pattern that's used in like Compose UI. It gives some form of a frame clock to it. So in coroutines, when you create a scope, you could add your dispatcher, like coroutine name. They're all part of your context, which is a set of things. And monatomic frame clock is a coroutine context element, which is why I'm able to basically do this, do a plus in there, add it using the plus operator. So there are two types of frame clocks that are part of molecule. There is the immediate that you would use for testing. There is also context clock that you would use. Normally, you would also always use context clock. And so I'll go into what these are. So basically, a context clock, what it does is that when you use that, it fishes for the frame clock that Compose is using. Basically, it leverages that one. It also means that it's going to use the monatomic frame clock from your calling coroutine context. And I'll share with you with a test what that means. So the way this adds basically a frame clock is that you see there's an empty coroutine context added for the context clock, and then my colleague, Bill, who made, first I want to say that Bill, my colleague, he makes, he leads, using coroutine best practices, and he came up with the gated frame clock, and I'll share also other things that he contributes a lot to Turbine and to Molecule to help us write better coroutine tests. So shout out to you. So let's look at, I want to share with you an example of a test that this library has, and I'll share with you what a context clock really, one of the properties of a context clock. So one of the tests this library has is basically utilizing a broadcast frame clock, which is useful for low-level operations. Now, you won't really use this. Normally, I'm just using this to explain to you, the behavior of a context recomposition context clock. So over here, I have a test coroutine dispatcher, and I have a clock, and I'm going to create a scope and add that to my context using the plus operator. So keep that in mind. So then I'm going to launch a molecule, and what this molecule will do is that that is going to update this mutable value mutable variable called value. So I have a callback right there in which I'm updating this value. And then what I'm going to do is inside of this launch molecule, I have just a mutable state of a counter, basically. And then this counter, on what I'm doing, this launch effect is delaying and updating it again and again. So we'll walk through this code as I advance the dispatcher. So suppose I do dispatcher advanced time by. What that's going to go is that it's going to go to this delay right there. And then it's going to go pass by it, because I'm using the delay controller in the coroutine test library. It's going to go past and go and increment this counter right there. And so so it goes through initial composition, that composable function gets called, and this assertion passes. So when I do advanced time by one more time, it's going to go to the delay, go past it, and then increment non-value again. Or if I do an assertion, this time it won't succeed. It won't succeed. And the one thing to note is because in the clock that I passed in, this is the clock that I'm using. This is the clock that was given to the recomposer. And this clock, I need to signal a frame. I need to do send frame and 0 some time. And then, my assertion would pass. So the clock is very important because this is the pull signal. And that's important to understand. So this is normally what you would use, the context clock, and this was the part of molecule that's in the first is challenging to understand for me. So the other type of clock is an immediate clock, which will basically send frames as fast as possible. And this is created by my colleague, gated frame clock. And as the word suggests, it has a variable which allows you to pause, basically sending frames to pause it. And internally, when you initialize it, you'll see that it reads from a channel, and it's always listening to it and sending frames to it. But you also have this gate to be able to pause it. So that's something I'll show you would use for testing. So there are two types of recomposition clocks that you could specify with this. So this is the step right there, is that to launch a molecule is that you specify a scope, and it gives you a flow, and then you specify a clock. And the clock you would use for non-tests is context clock. But you could also specify your own by adding it to the scope based on your use case. And you specify a composable function. So these are the 3 steps. And so what I want to show you now is how do we use it as part of our architecture, and show you some design patterns. And in our architecture, and I won't share the whole thing, the whole cache architecture. There were other presentations like yesterday that shared different pieces of it. So we have a view in our architecture. Obviously, we use Compose UI in so many different areas of the app. My team entirely Compose UI. And before Compose UI, we had a library called Contour, an open source library that we used. So we do not use fragments. We use custom views. And our views, there is a funnel that's an infrastructure set up that signals events. There's an event receiver to our presenter. And our presenter, it returns a UI state to the view, some form of UI state. And the presenter, it communicates with remote server, it could communicate with the database, etc. So when you look at this architecture, when you think, a lot of people, when they think of presenter, you may think of MVP, but this is not really traditional MVP. This is very reactive. It's very reactive. Also to note here is that this is not one of the good things of our architecture is that it's not a heavy architecture. It's very simple, very pragmatic. It allows teams to be autonomous, and that's one of the big pluses of our architecture. In order to come to Molecule, we also had different things before that. We had something called State Store, etc. And through different iterations, we converged on this on this architecture, on this pattern, and we're evolving it as we go on. So all our presenters, they all abide to this interface, a Molecule interface. And this interface, when you look at it, it has 2 generic types: an event that you from the view side that you would get, and it returns a model. So all the presenters, they all abide to this interface. And why is that? Our presenters, they participate in DI, so you could inject things to repos or databases, inject it to this presenter. And the models method is our composable method that we give to our Molecule. So let me give you a simple example of a pattern of reading from a repository, like something we regularly would do. Like you have a repo, and then you want to get some data to it and generate a UI model. So you could do something like this, where you have a remember on what the data is going to be, like some profile data, and then you use launched effect inside, call a suspending method like get profile data, and also very important to, in there you should do with context and change the dispatcher. So based on that, based on the data, we generate some form of a UI state, loading or success. So there's something else in here. You see the events flow. How do we read from these events? So what we do is that we as you saw in the example, we launch our molecules. Now, when someone builds something, they don't have to worry about this. We have infrastructure utilities that handle launching molecules. And another thing is that if you're using Android X, for example, you could do this, launch molecules inside of your view model, Android X view model, and create your own scope in there. And so then we call presenters.models and then give an events flow. The events that you would give, like you had a profile event, like an edit, you click on the edit button. So what we do internally is that we have infrastructure in which we launch a coroutine, we set up a channel that we're funneling events to, and then we convert that from that channel a flow, and we pass it to this presenter. And we're funneling events to it. So this is part of our infrastructure that we set up. The way we listen to events, we use the launched effect, and then we call events. You could do analytics tracking, for example, when edit button is clicked, or you could do navigation. We have a navigation infrastructure. So my colleague yesterday, Benoit, he gave a presentation. You should check out the recording he goes more in depth into these things. And we have our utilities that make things simpler. So again, my colleague Bill, he made these utilities, collect effect, collect events.
I can make that.
Oh, sorry. The git log was, so someone did, probably Jake. I think it's Jake. And when so we react to click buttons in the events. And that's a simple mental model, and usually when someone joins, they convert a presenter. Our previous presenter were observable transformers, and when someone joins in the onboarding process, they convert this and it gives them a mental model of how we set things up. This is a very simple architecture, and it allows us to go fast when we build things. The other thing to note is that our presenters, what happens when things get complex? We also combine presenters together. You could combine them together and to get separation of concerns. So suppose you're working on a page in which you have different components, and these different components are owned by different teams. And what you could do is to create if you have a lot of logic in your models, you could break that apart by composing presenters together. So you could have for each component, a presenter separately. And that really makes it simpler to reason about things. So then you could inject these presenters in your root one, and then combine them together. And then you could pass off what events that they need to be concerned with. So you could do events here, events.filter type, and then filter and then pass them to each of the components. And they return you a model that you could then bring it together. So on our complex screens that I work on, we use this pattern, similar pattern. So that's the architecture. So if you could also achieve this if you're using Android. We don't use Android X view models, but you could launch your molecule in there. Also build your StateFlow if you want. And so that's our architecture. It's a very reactive architecture. And the next thing that I'll talk about is how do you go about testing that? And So we have 100% test coverage. We don't write expressive tests. Yesterday, J-Rod, my other colleague, he shared how we use paparazzi. And we also, I'm going to share how do we add tests to our presenters. So how you want to test and what cases you want to test. You want to test based on different events. Well, does this presenter give you the right state, right? And there are a couple ways to do testing. You could use Turbine. You could also, there's a module that this library has, but we deprecated the extension. But because we recommend using Molecule because it works, it's better. It has a good API, and what we have. So what is Turbine? How many of you use Turbine? It's not that a lot, so this will be useful to people who don't use this. So Turbine is a queue-based testing approach, and it used to be, and how Turbine started was back in 2019. It used to be an extension, the SQL Delay library. It used to be a pattern that we used, and Jake and Alec, they extracted it out into a separate library called Turbine. And the name is Turbine because of flows. And by the way, the name Molecule, where does that come from? Is an analogy because you think about it, you think about a molecule like H2O, where you have hydrogen atoms. So our atoms in here are basically, these are our atoms, and molecule allows us to bind them together. It's a very nerdy, analogy, but it's good. So I wrote a blog post before this library was released, Kotlin Assert Flow Delay, which highlights the pattern that this library uses. The internals of this library have improved since its initial inception, and the API has improved. And so I'll share with you just the basics of what the API looks like. So the API, we have a receive turbine interface that has methods to await from a flow some event, some emission, or to determine what did it give an error or an item. So here's a basic example. So what this library provides an extension on a flow called test, and basically you could test these emissions, like a wait item gives you 1 or gives you 2. And the way this works underneath the hood has changed, and shout out to my colleague. I'm sure this time Bill worked on improvements in Turbine because I read the PR. And inside the way this library works is that it collects everything from a flow and it adds them to an unlimited buffered channel, and you could query from that channel. And so there's a method called collect and turbine that has a channel, and then everything basically gets funneled to it. And then there's a wrapper called channel turbine. This implementation was different, where before, when it added it to the channel, it used to box them in an event type. We still have that, but it's a little bit different. So, and then we have basically an API to can read from the channel. So when you're testing presenters, you could use this API, tap in, take advantage of Turbine. And Turbine, something else I just want to I'll add, is that my colleague, he added ability to utilize this API by creating wrappers around types such as int or any type that you want. So you could do Turbine right there, and then you could add things to it. And then you could use APIs such as skipping, or a wait item that Turbine provides. I would recommend watching his talk from Chicago Roboto, which goes much more in deep into why you would want to use this. So how do we use that Turbine, that API, to be able to test this presenter? And we want to test these different cases, whether the UI state was created correctly. And there are 3 steps. One is to use run blocking. So we don't use run blocking tests. I recommend watching his talk. He goes more in depth into why we don't use that. We use run blocking. We started to use run test also, which is in part of the new coroutine. You specify a frame clock, which is going to be an immediate, then you use the Turbine APIs. And here's an example. I'm going to test that. I'm going to test So we internally have utilities that make a lot of this wiring much more simpler. We have utilities where that does this launch molecule, and I'm using the test extension, and I could do a wait item, for example. I could also do assertions based on the event. So I could create a mutable shared flow, for example, for events, and pass and emit an event to it, and then do assertions that, that certain things happen. And we use fakes, for example, for our analytics, etc. So that's a very simple way to go about testing, and to testing your molecules. And it's a 3-step, very simple process of testing your molecules. So the last thing that I want to talk about is what I shared so far is how we use it in our architecture in a basic way, is how this library works underneath the hood. And this is more of an advanced part of the talk. I would be happy if you stay around. So this library is an example of how you could tap into the Compose runtime, and how you could use the Compose runtime to solve a specific problem. There's a pattern to be able to tap into the Compose runtime, to be able to set it up. And what this library does, this extension that it has, is not really a long piece of code. It's very, very simple. And what I'll share is how this library hooks into that. What are the things that you need to set up? So Compose UI, for example, is another library that hooks into Compose runtime and follows the same pattern, if you look at the source code. And there are 3 things that this library sets up, and any library that hooks into the Compose runtime sets up: composition, recomposer, and applier. But what do those things mean? I'll share with you just an overview. There are great presentations by Amanda, a friend who talked about the compiler internals that you should all check out. So Compose compiler is an inline compiler plugin, and when you declare something as composable, it does add some code to it. It does static analysis checks also. So when you annotate something as composable, it basically, what it does is that it teaches basically a composer on what nodes then needs to be added to this tree. And the reason why I'm sharing this is to give you a background a little bit on these components. So the way you connect to the Compose runtime is through this composer. So in this method, this is not the only thing that gets added. There's something else that gets added to be able to determine that a compose function is skippable or not. So this composer is passed along to every composer function that you call. So, and this is the calling context. This is very similar to suspending functions, where you have a continuation that you're always passing along from one method to another. And in terms of Compose UI, what this composer is doing is basically teaching the runtime, and is deferring it. Is determining what changes need to be added. So for example, you can see here it's using something called an applier recomposer, and it's telling it what nodes to be added. So this right here is, for example, the layout, this is important composable in Compose UI, that column and row, they all branch off of, called layout. And so remember also goes to that composer and determines whether a value is cached. What all of these things do is that they don't update something called a slot table directly. They create a changes list, a list of changes that need to be happen. And this also occurs when you do recomposition. What a changes is just a way, it has an applier. I'll go over what that is. It also has a slot writer. These are changes, they all get recorded and added to this changes list. How do these changes lists get updated? They get updated by applier. So Compose UI specifies an applier. This library specifies an applier. What that is takes these changes lists in batches and updates the slot table. And they determine what changed. So this is an example of the Compose UI applier. So the entry point of any client library there are 3 steps. One is to create a recomposer, specify an applier, and also to call set content method and to connect basically a composable function that you have to it. And this is the step followed, this is the approach that followed by client libraries tapping into compose. And what a recomposer is that it uses a context and it launches a coroutine to apply those changes in. So here's an example of Compose UI, the window composer class. It creates a context clock. So this library here has this method, and what it does is that it creates a composition. The applier doesn't really do anything in this case, and it's passing the frame clock as basically a context and the context element. And so the recomposer is very, very important. You have to tell it to wait for invalidations, and that's the next step that this library does, that it hooks into. And this basically starts the recomposer to listen for invalidations to be able to create the different changes when your presenter gets invoked again. And this is the most important piece of step, composition set content, which is calling the body. And when it returns the UI state, it gets passed along to this callback emitter, and that gets funneled upward basically to a state flow like this. So this is how it works. So where each time the composable function, it generates a new value, gets pushed to the state flow that you're reading from. So. And then you basically externally you're collecting from this. So that's how it works internally. There's much more in depth. I recommend a book called Compose Internals by my fellow GDE Jorge, who goes really depth into in 200 pages how all of this works. So that was my presentation. I hope that was useful. Making this presentation wasn't easy. We're very stressful. As always, any presentation. So thank you so much. It means a lot to me. I want to say thank you to my previous jobs, colleagues. It means a lot to me for you to be here. Just also want to say thank you to my colleagues from Peloton for being here, and for at Hinge, and also for my current colleagues. And so thank you. I hope that was, if you need help integrating this library, I'll definitely be happy to help you. Also anyone from Cash App. So thank you so much.